Hey, I'm Manuel, and I want to make a plea for a more mind-sized software design. I've worked in many different companies and positions over the last 12 years with the focus on iOS development. In that time, I've always worked with companies that would call themselves agile, with teams that would describe themselves as agile, that would practice some agile methodology, but it never was agile. Because agility is not some methodology, some framework, or some certification. Agility is the ability to respond to changes fast. Agility is a sports term. Agility is a physics term, and so let's not certification industry steal it. If it doesn't feel agile, it ain't agile. Simple as that. So why do we need agility? Changes can be forced upon us at any time. Changes in our business markets, in the strategic decision making of our company, technological reasons, or laws might be changed, and we need to adapt to that fast. Maybe we just have a few days or weeks to fulfill a certain law. If we design software with agility in mind, the design should not get in the way when it comes to the other tools that we use during in our agile processes. Also, it should support CI/CD workflows. So, guys, we need to be better at that. And we should maintain this agility at any time, and not only now and maybe a few months and releases down the road, but not after that. No, during the whole life cycle of an app, from being supported in the App Store till being not supported in the App Store. And of course, agility should be done in respect to inter-team processes, so that also other teams or team members, non-programming team members, can benefit from our increased agility as well. Oh yeah, my positive feedback loop. I do think that if we do start doing things better, then everything gets better. But yeah, well, probably another discussion. Also a very sensitive topic. So yeah, why is scaling so hard? I mean, I've not met one person who says, yeah, that's we are agile and it's great, and no. Well, I think because scaling is hard. Scaling knowledge work and scientific work is hard, and that's what programming is. If programming would be easily scalable, computer would be doing it. Simple as that. Because then it also would be easily automatable. But it isn't. And I want to illustrate. If our team would be of the size 1, the time to complete a project would be the time that it would take one person to code it. Well, makes sense. Quite logical. Not sure. But many people assume from that point on, scaling would behave like that you just divide the time that one person would need to finish the job by the number in the team, by the number of teammates. But it just doesn't work that way. Why? Well, I'm not the first person that tries to illustrate this. So on the left, we see a formula that I call the Kevlin-Henney conjecture, because I do know this through Kevlin-Henney. I'm not sure if he came up with it, but if he did not, I guess he would have named it somehow. But yeah, so this describes I think pretty well how scaling teams works in reality, and I want to explain why. So again, we have T1, and now after that we have this term in square brackets that is actually Amdahl's law, which describes how parallelization works, because you will always have an offset during parallelization, and this is expressed like this. And the second term after the plus sign is communication overhead times all the combination of connections between team members. And I think it describes very well. And on the right, I try to illustrate this. So besides the yellow stuff that is the work, we also have this Turkish turquoise color that represents the communication overhead, and we also see the connections. They are not complete, but we also see connections in the orange areas. So there are dependencies of the in the work. So not everything is parallelizable. So I try to illustrate it like this. So it becomes clear it is not simply adding more people and expecting that it will work. I've added this term P plus K equals 1 myself to express that I want to look at the relationship between the portion that is parallelizable in work and the communication overhead, because I think it's quite clear that if your code is not very parallelizable, you will have a lot of team sessions about it. You will have a lot of pairing sessions where you try to reason about the code with colleagues. So this is all this communication overhead. If we would plot it, it would look like this. So the y-axis shows the time that it would need that would be needed to complete the project, and the x-axis shows the number of programmers in this project. And this is overall project. So what we see is that there is a certain point, here indicated by red, where the curve turns around, and this means that actually by adding more people to the project from that point on, the project will more likely be more inefficient, so it will slow down. So by adding people, you effectively slow down the project. And red is this point of no return, and You should not use this formula to make any decision. It is just for illustrative purposes only. There are too much things going on in the real world that this could really express what's going on in a real team, but it's just the idea of complexity that it illustrates. But if we plug in some of the values, we will actually see what I think is a very scary scaling behavior, because if 90% of the work would actually be scalable, which is a lot, I think, by this formula, a third developer would already effectively slow down the project. And if you would have 10 times more, if you can parallelize 10 times more, which is expressed in the second line, you only should assign at maximum 4 developers to that. And I mean, this is a huge gap. And and to illustrate, in the third line, the third row shows that even if only 1 promille would not be parallelizable, then you could assign 10 developers. But I mean, that's, I don't know what code base would look like that. So this row could actually indicate that team sizes of 10 are just not sensible in any situation, and maybe some structuring would be in place. But I've also plugged in some very bad numbers. So and it's quite interesting that here I have not truncated the numbers, but rounded to the first decimal place to show that this conjecture actually would say that even the first developer would already be beyond the red point. So such a project of a parallelizable code of 20% or 10% or 1 per mil, as we see there, they are not viable, not in teams. But I do think that many projects that I've seen in my career are in that range. At least that is 20%. So and throwing manpower on that will only slow it down. That's the issue. But throwing manpower on it is the common reaction. But let's also talk about the architecture metaphor. So this is a slide why I dare to give this presentation this clickbaity title. I've noticed in several of my jobs that there is a danger in overstressing the architecture metaphor, and you can see I did not point out where the architecture metaphor might be a good one. In this table, I point out where it breaks, and I think we need to think about another name or another way of explaining what software architecture is. Because I've learned, especially since I started freelancing, that people think that architecture is something that they have to pay extra and that it's not really needed, but and that is something that is done beforehand and then executed and then doesn't contribute to the investment anymore. And I mean, that's just not the case for software architecture. So I want to point out that where it breaks, and that I think we should give it a more appropriate name, and which in my opinion, would be if we would talk about coding strategy, because a strategy is very abstract at the beginning, and so people cannot overstress this. well, yeah, and we know that strategy can be very different things. It can be a military strategy, it can be a political strategy, economic strategy. So yeah, people are used to this, and yeah. So instead of architecture, I want to talk about intrinsic design, and I do believe, and I do believe that what you see now on the screen is the design underlying every interactive app. The user interacts with the user interface, which triggers the logic to recompute state, and the new state is represented in the UI. It doesn't matter if we are coding in functional programming, structural programming, logic programming, or object-oriented programming. The underlying intrinsic design is always this, and therefore I do believe that everything that diverges from this intrinsic design must be considered additional complexity, and if this doesn't serve any purpose, it must be considered accidental complexity, and this is something, and accidental complexity is what we want to avoid, because accidental complexity is what creates bugs, because it's something that is not designed, it's something that is not really under our control. It's where the bugs live, I used to say, and we want to minimize it. I don't want to say at any cost. That's not the right choice of wording, but I think we should design apps that makes it hard to develop accidental complexity. Any code that doesn't express the intent of the app's designers, so I do not mean user interface designers, but all people that are involved in creating the app, if it doesn't express their intent, and I also do believe that we have a lot of source codes. We are very bad at removing codes. We are afraid, even though we have it under source control, we are afraid of removing codes. We are afraid that we hurt people's feelings when we remove codes that we do not find useful anymore. And also a lot of dead codes. And one thing I also want to talk about a little bit is what I call band-aids here. These are things that were introduced to cope with flaws in the language designs. And these are, for example, everything to do with visibility of things, of visibility levels, and for example, it might be a keyword that is introduced, like final open. I think everybody knows that a class that would be final from default would be much better. But instead, we have to finalize them, or other way around on APIs. And patterns are band-aids, because when we look closely at patterns, then their sole purpose is to deal with the fact that classes, which are the main tool used in modern object-oriented programming, don't have a concept of output. So you cannot just return something from a class like you can from a function. Instead, you have to implement certain patterns to cope with this missing feature of a class, and we have developed many patterns to do so. And I think patterns are cool. They are fun. It's always great when you learn something new, but they also tend to make the code very fragile, because not everybody understands every pattern in the same way or is aware of them, and so it's also a tremendous training amount to teach patterns to teams. So let's have a closer look at classes. So classes are certainly the most versatile types we have at our disposal. They are mutable, they offer inheritance, and they offer any number of inputs, because I can implement any number of methods and setter or whatever. We've talked about how outputs and patterns relate to each other. But I want to point out that any of the above points mean complexity, and if it's something we don't need in a given situation, then it's accidental complexity, and it might work for you, and this might not be a problem for you in the present, but this extra surface area might lead to deterioration in the future, and maybe just because some experienced guy is in vacation. Classes are pretty much unconstrained, as we've seen, but we know that good software design is about good constraining. We know it for structured programming, which actually was we know it for structured programming, where actually the article "Go to consider it harmful" can be seen as the starting point of a formalized version of that. Functional programming was actually invented to constrain mutability, and for similar reasons, OO programming was invented by constraining visibility. Functional programming uses a global state, but immutable one, while OO uses mutable state, but hidden one. So it's two solutions to the same problem: mutable global state. It's about constraining. But we learn classes should not take central roles in our designs, because they are too powerful. Because with great power comes great responsibilities, and when we put human irrationality into the mix, well, it can be tricky, and this is why we see code bases deteriorate, why we see our agile processes not working. The base is just not given. So another look at the class in comparison to a function. What I want to say with this one-to-one is that in a function, you call a function once and it will return once, while with object orientation, I actually should not call that. Yeah, well, we are looking at a class here. While in object orientation and with classes, we usually have an end-to-end message sending pattern. We have very different, in different languages, we have very different ideas what message sending is, and I think a lot of languages actually do not get it very well. But usually object orientation is defined as message sending, and there we have an end-to-end relationship, meaning a message sent from one object to another does not have to invoke a response, while it can. It can also invoke more than one response. Think downloading progress, something like that. Yeah. So we actually want this communication pattern that we know from object orientation, but we also want to be as mutable as possible, and we also want to be as constrained as possible. So we want to have handrails. We want to have tracks that we can move on, which we would be better suited with a function, but function does have the wrong relationship for request and response. So what's the solution? The solution is actually something that in at least related terms is researched since the 1890s, so predates object orientation and functional programming by a lot, I guess. Because this is actually related to currying. Currying is, in mathematics, is the act of splitting up multi-parameter functions into multiple functions with one parameter each. And partially applied functions are very similar in that regard, in that that you have a similar structure and you call those functions to different points in time. And yeah, so what we see here is a function create to-do list feature, and it takes an output parameter as an input, as a parameter, and it returns an input. So input and output are basically the same function type. We just use different names here to indicate the semantics, that once we want to use it as an input and once we expect it to be an output. I will not go into this much deeper at this point. I want to show you some code later, and then I will cover this. So let's add this partially applied function to the mix, and we actually see that we now got what we wanted. In the architecture that I will show you in a bit, I will use this construct to create the module type feature that I will show you in a bit. So yeah, Core UI is the name of the architecture. Its interface is actually a command interpreter, which means that on the top level, the surface area is only a function call that you can perform. Core UI has strict unidirectional data flow, which is very helpful to keep code reasonable, so to keep it mind size. As in every good architecture, the UI is really treated as an I/O device, so there is no other connection between the UI and the rest of the app than message sending. The different parts do not know anything from each other. They are truly separated. And in Core UI, everything is a module. And what I mean by this is that we have at maximum one input, at maximum one output, and we have and every module in Core UI has a DSL. Modules might share a DSL, which allows them to exchange messages, while others have their own DSL system, as in this case it supports separation of concern and true black boxing, and which also leads to a lot less necessary unit tests. Core UI is based on use case, which is not something I invented, but is introduced by Robert C. Martin in his clean architecture. So if you Google for it, use case clean architecture, you will find a lot of implementations in any useful language, and a lot of documentation. This is a very well understood pattern. Yeah. So this is the overview of our Core UI app. The top is the app core. We see really close by the UI. The next level is are the features, and then the rectangle, first rectangle layer are the use cases, and the use cases in Robert C. Martin's design use something called gateway, and call stack and store are such gateways, and yeah. So let's have a walkthrough where I want to demonstrate how information flows through this app. So in this case, an event is fired from the user interface. It's handed over to the app core. The app core level only does one thing: forward any message it receives to every receiver and feature it's now. UI is a receiver, and the features I've explained you. So the message that comes from the UI first is sent back to the UI, and then it is sent to every of the features. If a feature recognizes the message, it will react accordingly, and most likely create a request for a use case. And when a use case is finished, it will trigger sometime later the response. But I want to mention that a feature might use several use cases to finish one message, to respond to one message. But we will keep it with a simple case here. So the start call use case signals via a response that the call is started. The calling feature then creates a new message, hands it over to the app core. App core again will inform the UI, and then every feature, and the circle is completed. So we went from the user interface triggers event to the logic processes a new state, to the new state is represented in the UI. So it is pretty much exactly the intrinsic app design. Now I want to give you a little demo. So this is the app I want to show you. It is a simple to-do app. You can enter to-do, you can tag them, and simple journaling is kept. So let's enter a to-do. Buy beer. Okay, we can also My computer is a little slow. It's a 5 or 6 year old machine, and the simulator sometimes wants to be a little bit odd because of this. So we can add a to-do date. We want to have beer for the weekend, so let's go shopping on Thursday. Okay, it knows a little bit more, but I think this is enough as a presentation. So now let's implement a feature request from our product owner. So the feature request is that we want to make a to-do item forkable, so that you can take an older one and say fork it, and you have a copy of that. And then a second requirement, we also want to be able to pass in changes, so that we can fork it, but we can change, for example, the title while we fork it, and everything else is forked as it is. I am not the fastest typer, so I have prepared everything as in Git. Okay, now I'm checking out the next commit, and this commit should contain the basic specs for our forking. So what is a spec? A spec is a kind of test, and in this commit I've added this forking test. So let's try to run it, and of course it should fail. Yeah, so of course these tests do not work, because our to-do item, our to-do item doesn't know anything about forking yet. So this is our to-do item. It is a truly 100% immutable data type, and the way I achieve this is by reprocessing the data, by recreating the data for every change that needs to be reflected. In this alter methods, which are fed by with this change enum values, with these ones. So you can change the text, the completion date, and the completion status and the due date. The other values here are not cannot be changed by the user at this point. So now let's implement it, and of course I've also prepared that, because I'm really not the fastest typer. And I want to point out the changes. So we have added a change case fork here, and we have added it down here, that if it is fork and it comes with assigned changes, then a new item is created with a new ID. So that makes it a separate, distinct object, while the rest stays the same. And then we call alter with on it with the changes that might have been passed in. So of course the list also can be empty. And also in this private alter function, we deal with the changes. So for example, if it is a fork, then we always pass we always return the changed item. But if it is equal for all the content in it, and the change that we just have applied have not changed anything. We actually decide not to return the change item, but the self item. But that's an implementation detail. Yeah. So maybe we have a look at the test, how we can use those. So here we have the to-do item spec, and here we create a to-do item, and these are tests written with the frameworks Quick and Nimble. And if you're not if you don't know them, have a look at them. It's a great project. I really love to work with this setup. Shout out. So the way it works is that the tests, which are actually inside these closures, are executed in isolation, meaning that for each test, all the layers above are called independently. So, and the tests are actually the names are concatenated. So this test full name is actually to-do item underscore some underscores. I will forget about the underscores. So to-do item, altering check item, changes completed. So check item means I check it to be completed. And on the right side here we have what we expect. So we expect that the new completed value should be different to the original one, but ID, text, and everything else should not change. I want to. So that's how these tests works. But I actually want to point out how we use this alter function here. So it's just that we on the original to-do item call alter, and then we can hand over any change that we want to see reflected, and it will return the new value. Now we have added the forking, so we can also inspect that. So spec, it's not only a test, it's a spec, so you can inspect stuff. So here, for example, we can also see that the alter method can take a variable list of values. It could also be invoked with an array. So now let's have a deeper look at the forking specs that I've just applied. So first we create a new original to work on. We see that we can apply several changes at once. And now we fork it with no changes, and we expect it to have a different idea, but the rest is gonna stay the same. So let's run the test as we have applied the git command, the last git commit. So we see that all tests have run successfully. We actually have 176 tests. So, of course, with all these small tests, it's also very easy to write a lot of tests. And I mean, many of this closures here, you could copy and paste. Well, that's what I did. So yeah, it's also great to have a lot of confidence in your tests. And I also want to point out that you should not look at your test coverage so much, but I want to point out that with this coding style, it is easy to get a lot of test coverage very fast. And I think that is a valid metric, not the test coverage itself. It doesn't matter. It's not important that you have a very huge test coverage, but it's very good if you can reach a huge test coverage very fast. And with this architecture, it's very, very easy. So let's go back to the to-do item implementation itself. Where is it? So now that we have seen forking in the test in action, let's see the implementation. So we have this alter function here. If it's invoked with a fork change, then we will actually immediately return the changed item. And if it's not a fork, then we will check if it's if the contents are the same, because we actually don't want to return the new item in that case. Forking itself works like this, that a new to-do item is created with a new UUID, but with the self's text and other data points. And if there are changes, they are applied to this to-do item immediately by calling alter on it. So if the list is empty, nothing will happen. This is pretty much everything that we have to do outside, that we have to do in the state. The store will handle everything automatically. So now we want to connect the user interface to it. So what we need is that we need to have a fork message. So our message is to do fork item with and fork model. So which describes the stuff as a model. So we want to separate the message enums from all other DSLs. So we could be tempted to just exchange the information that we have for forking at different places already, but I introduce a model here because then we have a much clearer separation, and it's also much easier to implement certain protocols. So this is the message that we have to send to indicate a forking. Now we need our to-do list feature to react to this fork message. So we do this down here. And we call the use case, the fork to do item use case request method with a request with a request fork fork item with a list of changes. And here again we have the full implementation with an interactor class. Again, everything is totally black box. And if we request the interactor to fork, it will actually do so in here by altering the item, and in this switch we translate the model that we have introduced, the fork model, to the appropriate DSL values. Then we change the store by adding the item to it, and then the use case responds to its feature by informing it that the item was forked indeed. Which actually means that we will end up in this place where the response is once again checked, and now it's translated to a message that all the that the user interface and all the features do understand. And we also write a journal entry by triggering a message to do that, but I won't walk you through that. It works pretty much the same. So now the only thing that is missing is the user interface, which ironically we already have implemented somehow, because in the user interface we do exactly the same as we do in the tests. So that's why they are specifications. So let's already compile the new version of the app to make and look at the code at once. The user interface is connected via a view state. It's for SwiftUI, so it uses this observable object implementation. It does nothing special. It processes any new state it receives and informs the user interface through this published items. So let's look at the implementation. So we have a list of to-do item cells here, and the to-do item cell is implemented in this file. And now the forking is implemented if let's look at it. So now our context menu also has a fork submenu. And now we want to remind ourselves for a week later that we want to buy beer, but we want to buy beer urgently. So first we give it another title, and now we change the due date. Or we change the title, or we fork with a new due date. So pretty much as we would expect. How does it look in code? Here we have the context menu. If we want to change the date without forking the value, the item, we do this. So we say it's not forking, and if we want to change the due date for a forked to-do item, then we say yes, it's forking, and we want to present the date sheet as in the other way. So the date sheet is then presented over here, and depending on if it's forking or not, we send out to do fork item with the change, or to do send the message to do change due to this other value for this certain item. And we do very similar for the text changes. So, with very little changes, so let's, I did not prepare that. It were really only a few lines of code that we changed, and pretty much only additive code. We created new value for the user because, they requested it, now they can do it. And it's been done. Yeah, I mean, I am not a Swift UI expert, so I did have to figure it out. But if I were a little more experienced in Swift UI, I could have written this addition in a mere 10 or 15, 20 minutes. And you will encounter a lot of use cases in this scope. Other will be a little bit more effort, but I do believe that in usual terms, use cases will require less than a day to be implemented. Yeah, we have talked about model and state, also the store. The funny thing about the store is that although it acts a little bit like a class object, it actually isn't neither a class nor a struct. And I want to show you what it is. So I decided to go also here a little bit out of the ordinary, and I must say that after using this pattern in 3 apps by now, I am very happy with it because it's just simple. So what we see here is the declaration for the store. Usually you would go to a class for a store. It's you need a reference type, so struct wouldn't work, and certainly a class would be the go-to type. But for the same reasons, I didn't want to have a class in the central of my architecture. I also didn't want to use it for a store, so I came up with this construct. Store is a tuple of functions, 5 functions being access, change, reset, callback, and destroy. And store is the composition of those functions bind together in a tuple. Is it tuple or tuple? I never know. So this is just a declaration. This is something that we definitely need to implement. So how would it look like? Here we have a create disk store function that implements this tuple for usage on a persistent storing disk, for example. So again, so this we have this function that returns the store. The store is this tuple, and in place we implement the functions. We say, well, state just returns state. Remember, in single statements function, you don't need to use return anymore if you return. So this function returns the state, so it's just the access of the current state. The change function applies changes that it received by forwarding it to the state, which is then written to this variable. So this is the only place in the app core where we need mutability. So this declaration and these three statements for change, reset, and update are the only mutable statements in apps, in my app core, so in the features, in the use cases, and in the state and model. So it's very powerful, yet if you get used to it, it's also very simple. Well, then it's persisted to store and so on, and the private implementations for the store persisting, for persisting the store, destroying the store, and loading the store are found down here. So they are not accessible anywhere else. So this is the only interface we have to create this store. To create another store, you could just implement another function and maybe have a core data store. If you know